Welcome back. In this video, we will be solving linear congruences, and the main result of this video is this one. Let's let a and b be fixed integers, and let n be a positive integer, which is also fixed. The linear congruence ax congruent to b mod n has a solution if and only if b is divisible by the GCD d of a and n. Moreover, if the GCD d of a and n divides b, then there are d distinct solutions modulo n, and the solutions are congruent modulo n over d. Okay, so let's prove this theorem. Since this is an if and only if statement, we have to prove it in both directions. Let d be the GCD of a and n. Assume that ax is congruent to b mod n. If that's the case, then ax would be equal to b plus a multiple of n. And solving for b, we find that b would be equal to ax minus nk. And now, since d is the GCD of a and n, it means that d divides both a and n. So we see that d divides the right hand side here because d divides a and n. As a result, we see that d must divide b. So we have shown that if ax is congruent to b mod n, then the GCD d of a and n divides b. Okay, so we have proved the statement in one direction. Let's do the opposite direction. Let's now let's first do this. Let's first apply the extended Euclidean algorithm to express d as a linear combination of a and n. So we know that by the extended Euclidean algorithm, there are integers s and t such that as plus nt is equal to d. Now let's assume that the GCD d of a and n divides b. So if d divides b, then b is equal to a multiple of d. So b would be dk1 for some integer k1. Now this equation right here, let's multiply the both sides of this equation by k1. And if we do that, we get ask1 plus ntk1 is equal to dk1. Now dk1 is b, so we find that ask1 is equal to b minus ntk1. Now replace sk1 by x and replace negative tk1 by k. And if we do that, we see that we get ax is equal to b plus nk. So we have this equation for some integers x and k. But that simply tells us that x is congruent to b mod n. And so we have shown that if the GCD of a and n divides b, then ax is equal to b has a solution. Now let's tackle this second statement here. So we want to show that there are d distinct solutions modulo n, and the solutions are congruent modulo n over d. The first thing I'm going to do is show that the solutions are congruent modulo n over d. If x1 and x2 are solutions, to AX congruent to B mod N, then AX1 would be B plus a multiple of N, and AX2 will be B plus a multiple of N as well. So AX1 is equal to B plus NK1, AX2 is B plus NK2 for integers K1 and K2. Okay, so let's subtract the second equation from the first. If we do that, we get AX1 minus AX2, which can be written as AX1 minus X2. And then when we subtract this from this, we get NK1 minus NK2, which is N times K1 minus K2, because B cancels out. So we see that A times X1 minus X2 is N times K1 minus K2. Now I'm going to divide both sides by D. And if I divide both sides by D, this is what we get. Now notice that the following. A and N, the D is the GCD of A and N. So if I divide A and N by D, A over D and N over D, their GCD would be 1. So that is A over D is relatively prime to N over D. So which means that they don't have any common divisors, or they don't have any common factors. So from this equation though, we see that N over D divides the left hand side, because the left hand side is a multiple of N over D. So N over D divides the left hand side, but N over D has no common factors with A over D. As a result, N over D must divide X1 minus X2, which means that X1 minus X2 is 0 modulo N over D, which tells us that X1 is congruent to X2 modulo N over D. So what we have shown is that if X1 and X2 are two solutions of the linear congruence here, then the two solutions are congruent modulo N over D. Okay, so basically we have shown here that all solutions are congruent modulo N over D. So let's let X be a particular fixed solution of the linear congruence. Then from the previous slide, we can say that all of the solutions are congruent to X mod N. So all the solutions are of the form X plus N over D times K. Because all the solutions are congruent to X mod this, that means all the solutions are of the form X plus a multiple of N over D modulo N. So now in fact we obtain all the distinct solutions when K varies from 0 up to D minus 1. So when K is 0 we get X, when K is 1 we get X plus N over D, when K is 2 we get X plus 2N over D, and so on. Now of course when K is D we get back X, because when K is D you get X plus N, but X plus N mod N is the same as X mod N, so you get back X here. So, and then if you take values of K bigger than D, you just repeat the same values here. Now all these values here, they are no two of them are congruent modulo N. So there are D of them here. So these D solutions are distinct mod N, and of course they are the same modulo N over D. And Okay, so this is just a short note here to show that, if x is a particular solution, then x plus n over dk is also a solution mod n. So if a times x plus n over dk is equal to ax plus an over dk, that's the same as ax plus a over n a over dk. Now this is modulo n, this is 0, modulo n, this is b. So we see that x plus n over dk is a solution of this congruence modulo n. Okay, so that's the end of the proof. Let's now do an example. I guess yeah, let me stop the video here. In the next video we will go over an example.